Okay, question 9. This is a tough question. So I consider this to be certainly up there in terms of the most difficult of questions. So there's an alternating current of, as in the whole of question 9, alternating current of 3 amps. So I'm just going to sketch myself. So it's 3 amps input into the primary, 6 amps out. So for that to take place, this has doubled. So the voltage, which is the question, calculate the size of the voltage. This must have halved. So in the secondary coil, after the secondary coil is halved. So across the secondary coil is half the size D. Explain how an alternating current in the primary coil causes an alternating current in the secondary coil. So I'll draw it this time without the soft iron core, because these work without a soft iron core. So now we know when we put an alternating current in, this induces a changing magnetic field. That then cuts these coils. Okay, so the change in magnetic field cuts the coils, and then this induces a voltage, and if it's a complete circuit, we'll get a current in amps. So now let's turn all of that into words. So the alternating current induces a changing magnetic field in the primary coil. The changing magnetic field cuts the secondary coil. This induces an alternating current in the secondary coil, or induces a voltage. We can kind of use those interchangeably there. So that's that question done. Now I've got one of these tricky transformer calculations. I'm going to do this in a range in 3 different ways, and you try to pick the way that's best for you. A primary coil is connected to 230. So if I just sketch this now, I'm going to put my primary coil on this side of my secondary there. I've got 230 volts in. The voltage is 15 volts out. So we know this is a step down transformer. The primary coil has 600 turns. So let's put loads of turns there, and this is going to have less. And it's calculate the number of turns on the secondary coil. So you can either do it using basic ratios of the 2 things that you have information for, or you can use the equation that's in your booklet, and you choose whichever way is best for you. And then there's 2 ways of going about using the equation in the back of your booklet. So that's what's going to be in there. NP over NS equals VP over VS. We want to get the number of turns on the secondary coil. So if I just go through, we want this. So we need to divide both sides by MP. That'll get rid of that. And MP divided by MP is 1. And that's the mistake that students make. So now we're left with 1 over NS equals VP. You can see that on top. VS and NP is now under here. So now we can substitute the values in. VP is 230. That's the voltage we put in the primary. Divided by 15 times 600. All of that equals 0.0255, and then I just take the inverse function of that. And that will give me 39.1. Or, here's the other way of doing it. Rather than be left with 1 over NS and do that, I can actually just flip those 2 over. So you can see VS over NP's gone on top, VP's underneath, and that will give me the same. So that's method 1, method 2, and then method 3 is just find out the unitary method for the 2 bits of information you've got. So we can see now 230 to 15 is a ratio of 15.33 to 1. Now we know that, well, we know this is a step down transformer, so I just take this unitary ratio and I divide by that. If it was a step up transformer, I'd need to multiply to get the secondary coil. So tricky question. I've given you 3 methods. 1 and 2 are a play on each other, and 3 is another way of doing it if you don't like using the equation. Now, what I consider to be one of the hardest questions for you to answer. So we've now got a alternator, and we can see that there. And the reason we know this is an alternator is we can see we've got slip rings rather than a split ring commutator. And for this one, I'm just going to go through slowly through what's going on, but we can see peak voltage is at Q and it's 0 at P, R and T. So the crucial part to this is When the coil is perpendicular, that's going to be Q. When the coil, imagine that's the coil, is vertical, that will be the zeros. Because if you imagine the magnetic field lines going across, when that moves up, it's going to cut lots of field lines. That's going to be the highest amount of field lines we can cut. Imagine the field lines going across here. We can see that when that moves across, it's parallel. There'll be 0 volts there. So now we're going to turn that into words with a model answer, and I suggest you learn this off by heart. Make a cue card, really go to town on it, because it's a tricky question. So the coil will cut the magnetic field when we move it. The coil will experience a changing magnetic field. This induces a voltage in the coil. So there's 3 easy marks for that part, but then we've got to now explain the graph in terms of one complete. So when the coil is horizontal, the greatest number of magnetic field lines are cut, so there's highest voltage. That's point Q. So we can see that this started at 0 volts. So the coil was actually, so if we imagine this is the coil there, it would have been horizontal to it at the start. When the coil is vertical, it is moving parallel to the magnetic field, so no field lines are cut. And now we can point out that that's P, R and T. So this will lead to 0 voltage or current. This is points P, R and T. And that's probably my simplified way of explaining that. And there we go. And good luck with that one. Learn it well.